Thank you very much for having me and also for the opportunity to speak. So I was asked to speak about canonical metrics with in Kähler geometry with a strong emphasis on metric geometry and metric completion. So that will be kind of the focus. That style will be, at least I intend to give sort of a colloquium style talk. The only drawback will be perhaps there will be very little emphasis on recent results, but hopefully the picture will be rather complete. Okay, so helped a little bit. So Valentino introduced a lot of things, so maybe I can just still recall one or two of them and gloss over the rest. So we'll be working with compact Kähler manifolds, and we'll be nailing into ground a background metric omega. So what this really means is that omega is a 1-1 form, and near every point on a manifold, you can find a neighborhood and a smooth potential. Oh, sorry, this should be the smooth function should exist only on U, such that omega restricted to U is I del bar of G. So it's the complex Hessian of this real valued smooth function G. And of course, we're asking the matrix formed by these coefficients to be positive definite. All right, so as this was also emphasized, so given this construction, you immediately see that this form is closed, and as such, omega determines a de Rham class in the second de Rham cohomology group, and this will be a class in the Kähler cone. Now, this was also mentioned, so due to positivity of this matrix here, if you stick the complex structure J in the second component of omega, you actually get a Riemannian metric on X. So allowing to discuss curvature of omega, Ricci curvature, scalar curvature, as you typically do with Riemannian manifolds. So that's what we mean when I say reach some kind of curvature of the Kähler form. I really mean the curvature notion, corresponding curvature notion for the Riemannian metric that's composed by this construction. Okay, so moving forward, right? So let's suppose you have another Kähler metric on the same Kähler manifold. Let's say omega prime, and let's assume that they have the same cohomology class. So then by this non-trivial fact from Hodge theory, the del bar lemma, there exists a smooth potential, now global one, such that omega prime you can write as omega plus I del bar V. So basically, if you accept this restriction that you only care about Kähler metrics in the same de Rham cohomology class, then every new metric you can find, you can write it as the old metric plus the complex Hessian of a potential. All right, so this conveniently allows us to introduce this space. So H omega, so these are smooth potentials for which omega V, this expression here that also showed up here, I ask it to be positive definite. And as soon as you do this, what you get is an almost one-to-one correspondence between Kähler metrics of this type, having the same cohomology class as omega, and a certain class of smooth potentials. So this H omega will be an open subset of C infinity. So this is, as it was emphasized in numerous talks, a great convenient feature of Kähler geometry. To study metrics, you can actually study the corresponding functions, potentials on the space. Okay, so a starting point in this field is Calabi's question. So is it possible to prescribe Ricci curvature within this class? So if you give me any 1-1 form in the first Chern class, is there a Kähler potential here that has the same Ricci curvature as the form you've given me, or the equivalent question for volume forms? And this was answered positively by Yao and initiating a flurry of activity in the area, many of them showcased in talks in this wonderful conference. Now, today I'll be focusing on another question that I believe is also due to Calabi, and maybe not this specific form. So Calabi asked, is it possible to find a constant scalar curvature metric in H omega? I believe Calabi's expectation was that the answer for this question is yes, or maybe in a slightly general form of his extremal metrics. As we know now, this is not the case. So a reformulation would be under what condition you have constant scalar curvature metrics in H omega. And I will tell you part of the story that's rather complete. What's great about this question is that it lies at the intersection of algebraic geometry, PDEs, and differential geometry, so you have many angles on it. Today I'll be focusing mostly on the analytic PDE angle. Okay, so what Mabuchi noticed is that you actually have an energy functional that you can define on this space of Kähler potentials. It looks slightly unfriendly the first time you look at it. We won't be doing any sort of hard analysis with these terms, so at this point maybe you can just accept that there exists an energy functional whose critical points are CSCK metrics. It's rather a surprisingly hard theorem to show that actually these critical points are minimizers. I believe Boo will sort of address that when talking about his work with Berman. But I guess if you're a newbie to the area, you can just assume that due to some black magic, when you compute the Euler-Lagrange of this energy functional, it's exactly the scalar curvature equals constant equation. Now, maybe just a quick rundown. So the most difficult term typically is considered the entropy term here, and there's two other terms, and these are variants of the Aubin-Yau or the Monge-Ampère functional. They're down here. Again, if you're Kähler geometry, you've seen this a million times. If you're not, just think of some abstract functional whose critical points are what you're looking for. So really the question is, when does a functional have critical points? Well, various answers in various settings. Okay, so let me just start with a very vague conjecture, and then we'll make this more and more precise as I move forward. So we are trying to force a functional to have minimizers, right? So if we were in finite dimensions, right, something like this would be good, right? Something like this, obviously not good. So what we're trying to kind of force, we're trying to make sure that as we move out to the edge, or the closer and closer to, sort of further and further out in this space H omega, we want to make sure that this K energy functional sort of shoots up to plus infinity, right? Thereby, in some bounded region, forcing a minimizer, right? So vaguely, you can form this as properness or coercivity, and this is something that in PDE theory people formulate a lot. So vaguely, that's what we're looking for, and then we're hoping that this should be equivalent with uniqueness of existence of a unique minimizer. So let me just quickly tell you, I won't talk about uniqueness a lot. I think Boo will do that for me. So again, another convenient thing that I can just push under the rug. If there exists a minimizer, it's certainly unique. But when does a unique minimizer exist? Well, this is what we kind of want to characterize. So this is what we want. We want our K energy to look like this, so it gets the check mark that there's a minimizer there. Now, a weaker version of this that maybe at this point I don't even want to vaguely explain is that this K will be geodesically stable. I think after the next slide I can maybe come back to this. Now, thankfully, all these vague conjectures will be or are now theorems with the difficult direction due to Chen Zheng, and then I have some contributions on the other directions. I'll specify them later. Now, at this point, we're trying to formulate this conjecture precisely in this infinite dimensional setting. So we look at something as simple as possible. So finite dimensional case, so we're Rn, and I have a strictly convex functional capital F. So due to strict convexity, if F has a minimizer, it has to be unique. This is kind of what's happening also in our setting. Now, regarding the existence, it's an extremely basic undergraduate level thinking gives you this equivalence. So there exists a minimizer if and only if your strictly convex functional is coercive or proper in this sense, right? So F is dominated from below by the norm times a constant minus some other constant that doesn't have much meaning. And this is what we mean by geodesic stability in this setting, that if you give me a unit direction, so a vector on the unit sphere and any point, then you look at this ray x plus ty. Okay, so what I mean here, t going to plus infinity. So x plus ty, right? So for positive t, this is just a flat ray. And by geodesic stability, we mean that if you look at the slope of your convex functional under this ray, which is always this limit exists, when t shoots to infinity, not to zero, at zero this is meaningless, obviously, then I should be bounded from below by this constant c, and it's not hard to see that this constant c here is the same as the constant c there, and then you can call this some sort of uniform stability constant. Yes? Yes, sorry. Oh my God, yeah. So n, I don't want to write it, and infinity. Okay? Right. Now, I think it will be of great interest to give the quick proof, at least of equivalence between 1 and 2. It will give us a good idea of what needs to be done in infinite dimensions, even though it's, as I said, calculus level elementary. Okay, so that properness implies the existence of a minimizers. It's just a basic fact about Heine-Borel lemma, right? So you take a minimizing sequence due to coercivity, right? If you take a minimizing sequence, the sequence itself must be bounded. Hence, it subconverges to some x0 in Rn, and then strictly convex things are continuous. So there you go, you're done. Slightly more interesting is the reverse direction, right? So let's assume there exists a unique minimizer. How do you get coercivity or properness? Well, you take the unique minimizer x0 and put a sphere of radius 1 around it, and then you look at this infima, right? So the difference between points on the sphere minus, so the difference of your functional at points on the sphere minus your functional at the center of the sphere. Now, due to the fact that this sphere is compact and then x0 is the unique minimizer, this c must be always positive. And then now you use convexity, right? So for any, so you have this sphere x0 here, centered at x0, radius 1. So now you take a vector outside the sphere. So what you do, you join the center with this outside point x. So this will cut the unit sphere somewhere at the point y. And then you compare slopes. So the slope of your functional from here to here, it lies above the slope from here to here. And then that will give you the coercivity, right, down here. And then basically you're done. So you get the estimate outside the sphere, and then inside the sphere, the ball is compact, so you're done. Now, obviously this was very simple. The whole talk will be about how to imitate this very simple argument in our infinite dimensional setting, right? So right now, the whole thing is very murky, right? But there's 3 points of emphasis here, right? So we need a convex functional. Right now, I haven't said anything about that. We need some sort of compactness that always comes for free in finite dimension. No idea about that. And the space itself, right? I took a bunch of Cauchy sequences. Those all have to have limit. So I need to have some sort of completeness as well. So I guess 3 C's I need to focus on obtaining, right? So convexity, compactness, and completeness. Okay, so the naive attempt starts with noticing that H omega is a convex subset of C infinity, right? You have two Kähler potentials there. Convex combinations are also Kähler potentials. So you're hoping maybe the flat geometry should work. You take a flat segment, plug it into K, compute 2 derivatives, and it doesn't have a sign. So this is not going to work. And then the more serious approach was first noticed by Mabuchi and later on rediscovered by Semmes and Donaldson. So they suggest that we have this trivial Frechet space H omega, put on it a Riemannian metric that's non-trivial. And the hope is that along its geodesics, that will not be flat segments, this K-energy functional will be convex, and at least you're done with one of the things you need, and then hopefully compactness, completeness will follow in some shape or form. So this was their suggestion. So obviously here, if you take a smooth tangent, so the tangent space at every point H omega is just C infinity, because this is a trivial Frechet manifold, and this is the metric they propose, so it's an L2 metric. Now, what I noticed around 2014 is that maybe it could make sense to generalize this and consider different values of P. So have this kind of Finsler metric, where P now can be anything greater than 1. And as we will see later, various values of P are, so depending on what context you work in, you should pick a different value of P. We'll see why. So these three C's, so maybe I can cast this ahead. So compactness will not work in all P's. Now, the one good thing about, you have some flexibility here with the P's. So if you compute the Levi-Civita connection and the geodesic equation for all the different P's, the geodesic equation is the same. So even though you have different metric geometries, the geodesic curves, the length minimizing curves will all be the same. Okay, so there's some good news and there will be some bad news, right? So if you happen to have a smooth geodesic in this Mabuchi, Donaldson, Semmes geometry, you plug it into K, compute two derivatives, it's positive. So you're very happy. The bad thing is that, unfortunately, if you take 2 points, try to join those 2 points with a smooth geodesic in Mabuchi space, no such thing. So you again have to sort of adjust the plan, but it's not all doom and gloom. So for any two endpoints, one can define a so-called weak geodesic joining them with bounded Hessian. So I won't write it down. So this will become, so once you write down the geodesic equation between two endpoints, this will be a Dirichlet problem for the degenerate complex Monge-Ampère equation. And people over time have proved various estimates. So the first contribution here that was very, very important due to Shushong Chen in 2000. So Chu, Tosatti, Weinkauf have obtained the full. So Chen has gotten the Laplacian estimate. Chu, Tosatti, Weinkauf obtained the bounded Hessian. And myself, with my advisor and a postdoc, we showed that you can't do any better. So having a bounded Hessian is as good as you can get. So we have some sort of notion of weak geodesic. But what's going on, right? So you have H omega. This is H omega. And then you have two endpoints, smooth. And you have some sort of weak geodesic connecting them. But the weak geodesic leaves this space. So UT, T between 0, 1. This leaves this space. So this leaves in the space H omega 1, 1, maybe. So these are the potentials whose only thing we know is that this Hessian is bounded. So what to do? Well, you can do something. So what you should do here, and this is the plan that we're going to follow, we should extend H omega to accommodate these weak geodesic segments. So enlarge it naturally so that these weak geodesic segments will be in there. But what should be the enlargement? Well, since there's a natural candidate for a metric here, right? The associated path length metric. So in this case, I'm still going in for general P. Every smooth curve, the length you can measure in any Finsler space. And as such, you can introduce a path length distance. This dp distance between two potentials should be the infimum of the LP length of any two smooth curves connecting them. One can show, this doesn't come for free, is that this is a bona fide metric. The issue is that triangular inequality you get essentially for free, but non-degenerateness you have to work for, and you have to be careful in finite dimensions, path length metrics, infinite dimensions, path length metrics sometimes are degenerate. But in the case p equals 2, Shu-Sheng Chen showed that this metric doesn't degenerate, and then for general p, you pretty much get the same result following his proof. So, I mean, a natural candidate for an extension here, once you have a metric, right, is just compute the completion. And this is what I've done in this paper. Right, so maybe there's a lot going on in these two lines. So I computed the metric completion of the space, and I showed that it's equal to something that was already studied. So this is a space that was studied by Gedge-Zeryahi, and then much of the Gedge-Zeryahi study rests upon a work of Segrel in the local case. So thankfully, what I was able to show is that this is not just some abstract metric completion, but it's some sort of potential space that I won't give you the definition now, but at the end of the talk, I'll tell you as much as I can about it. Thankfully, on this space, which is the same as the abstract completion, there's a lot of potential theoretic tools available that was later used. I can maybe mention a few things about that. And the other good thing here, right, so coming back to weak geodesics, so this weak geodesic curve, right, that, at least in this case, only connected two smooth endpoints, left the space, this whole thing will be inside the metric completion. Moreover, inside the metric completion, so in this complete metric space, it will be a bona fide distance minimizing curve, right? So in metric spaces, for those of you that don't work with these on a daily basis, being a geodesic means that, right? So I'm looking at the curve parameterized by t. This is a geodesic. It means that all these distances are moving linear in time. Moreover, I mean, this is just an added benefit that's not really important. If you take two endpoints living in this metric completion, there's actually a weak geodesic connecting them that stays inside EP. So you really identified a class that's geodesically stable. Okay, so we gain completeness. Let's see if convexity survived, right? So what's going on? So I said, okay, maybe one thing before I proceed further. So later I'll try to spend some time telling you concretely what this EP space is. For the time being, maybe it's just a few reassuring words. So in case of Riemann surfaces, what I wrote here is essentially true. So for the value p equals 1, E1 is actually W12, the Sobolev space, W12. And for higher p, what I wrote is almost true. So you can think of these spaces, EP, as the appropriate nonlinear analog of Sobolev spaces that hopefully are the correct Sobolev spaces for our nonlinear problem. Okay, so completeness is out of the way. Let's see if convexity survived. Well, it turns out that the K energy, right? So the K energy functional was initially only defined on this space of smooth Kähler potentials, and there were three terms in the definition of the K energy. Thankfully, what's going on is that all those three terms, those functionals in the definition of K energy, oh boy. So all these three terms make perfect sense on these metric completions EP. It's not a coincidence that I grouped them this way. So basically, you have a natural extension here to this space. And then now, again, Boo comes to the rescue, if I can go back to where I was. Oh. Yes, so, right, so what Boo and Robert showed is that on these weak geodesic segments that have endpoints on smooth endpoints, the K energy ends up being convex. So we took that result, and using a not too difficult going to limit argument, you can show that also this extended functional to EP also becomes convex. So really what we have is, seemingly we have kind of the right space, EP, and we have a functional K on it that, at least if you believe me, it's a convex lower semi-continuous functional. So there's only one thing that needs to be kind of clarified. How about compactness? So this is the first time where you have to distinguish between P's. So compactness is known for the case P equals 1. And this was, I mean, it's essentially hiding in this paper BBEGZ, that predates all this study. They've formulated a compactness result that can be reformulated in this context in the following way, and this is actually enough. So the following set is D1 pre-compact inside E1. So basically, you take the K energy, so fix a positive C, and look at the sub-level set of the K energy under C, so the C sub-level set of K, and just look at it on a ball of radius C. So this is a D1 pre-compact set. Now, if you go back to the finite dimensional result I had, there we had obviously a stronger compactness result in Rn, right? That every bounded closed set is compact in Rn. This weaker version of compactness is enough to prove the same result. So I can almost state a general result. The missing piece is this formidable accomplishment by Chen and Chang. So minimizers of the K energy in E1. So now I'm saying, due to the fact that I only know about compactness in E1, just focus on E1. On E1, you have an elliptic regularity result. So if the K energy happens to hit the minimizer on E1, then that minimizer is actually smooth. So this is what they proved, that this was a fantastic result because it unlocked a priori estimates for fourth order PDEs that previously nobody even attempted doing. And of course, this is also in line with this kind of Sobolev space picture, right? So in case of Sobolev spaces, right, when you're dealing with Laplacian, you easily produce solutions of Laplace U equals F in Sobolev space. And then comes the harder part to show that that solution you produced is actually smooth or as regular as possible. This is the nonlinear equivalent of that in our setting. So with all of that, here's the result that replaces the vague reformulation. So I had at the very beginning. So all of these are equivalent. So there exists a unique CSCK metric in H omega. So there exists a minimizer. If and only if the K energy is proper. So remember, in the finite dimensional case, I had absolute value. Here, absolute value is replaced by the metric. And since compactness only works for D1, I am working with D1. So the K energy is bounded from below by this D1 distance times a positive constant minus another arbitrary constant. Moreover, this is the result of geodesic stability in this infinite dimensional setting. So when you give me so the K energy is uniformly stable along geodesic rays. So you give me a geodesic ray in this nonlinear world. Then if I look at the slope of this slope of this convex K energy, as t goes to infinity, it should always dominate a positive constant C. And again, this C here and this C here is the same. Now, so maybe I can just go line by line. So that the fact that the harder direction that this condition implies existence of CSCK, that was proved by Chen and Chang using this a priori theory that I just mentioned. The weaker direction was done by myself, Berman and Liu. And regarding the harder direction, we also pointed out that really the reason why we couldn't do the harder direction is because there was this elliptic regularity missing that was later on produced by Chen and Cheng. Regarding this result, there's contributions by Chen and Cheng here as well. So what they've shown, and this is again probably the harder result, that if you have geodesic rays in this space, so basically the completion, then this condition must hold and is equivalent with having a unique CSCK metric. My contribution with Liu Qin was adding bounded Laplacian here. So what we've shown is that you don't need to look at rays in this space. You need to look at rays in this space. So these are this is the space of potentials where you have second-order derivatives, but not higher. And this kind of wraps up this whole tour. And the only thing that I want to sort of emphasize in the remaining time that I have is what's this mysterious space EP here? I'll try to say a few things about it, make it as concrete as possible. All right? Any questions so far? This will kind of end this connection with canonical metrics. All right, if not much, then off we go. Right, so we're trying to understand what this is, this abstract metric completion. So the biggest space of potentials that one can consider in this context is the so-called omega plurisubharmonic functions, which, by slightly abusing precision, they're all defined in this manner. So you take an upper semi-continuous function on X, possibly taking up minus infinity as a value, right? And then you take this Kähler condition that we previously had, but you assume it in the sense of currents, right? So it's basically asking positivity in some sort of distributional manner. Now, using the theory of currents developed by Bedford-Taylor, I won't open this black box. So it is possible to extend the notion of volume measure. So if U is smooth here, this is just a regular volume measure. But you can extend this notion to potentials, even in this very nasty space. But there will be some loss of volume because I'm taking the non-pluripolar notion of complex Monge-Ampere measure. Those do not charge sets of zero capacity. Sets of zero capacity were also mentioned by Professor Zhu. And then because of that, I must have an inequality here, whereas in the smooth case, I have equality. And this is convenient if you want to introduce the so-called set of full mass potentials. So potentials U coming from this space that extremize this inequality, meaning you have equality, so extremize this inequality, giving you equality, those are called full mass potentials. Now, this EP class is a subclass of full mass potentials. So EP is the class of potentials in E, so full mass, such that this integral is finite. So you take the potential, you take the LP norm of the potential with respect to its own measure, that is finite. And again, it's a small exercise to see that, for example, in case of Riemann surfaces, P equals 1, this is going to be the same as Sobolev space. It's integration by W12, integration by parts. Okay, so let me give you some indications on why this space is the appropriate completion for the space of Kähler potentials. Right, so it's hard work to show this double inequality. So first, just take two smooth Kähler potentials, so U and V, and the claim is there exists a universal constant, C, greater than 1, actually only dependent on the dimension, such that you have this double inequality, right? So on the left, you see the dp distance between U and V, and on the right, you see the same thing. I raise it to the power of P, both sides, because I don't want to have P square roots in the middle. So what this double inequality says that these dp distances are essentially what? So they are basically some sort of LP distance with moving measure, right? So the dp distance between u and v is what? This LP distance between u and v with respect to the measure of v, and the LP distance of the same with respect to the measure of u. So it kind of gives you in essence what these things are. What's good about this expression is it's quite concrete. So remember, the dp distance was introduced in the following maybe esoteric manner, right? So you took all smooth curves between u and v, you computed some LP length, and you took the infimum of those, right? Fine for a definition, but very difficult to put your hands on. And now when we want to do analysis, understand the magnitude of dp, it's perfectly fine to just look at this double expression. And then as a byproduct of this whole thing, what you get is that this thing here, if you just define it as some sort of a quantity depending on u and v, it's actually going to be a quasi-distance because dp is a distance. So it's quasi-equivalent to dp. An expression that's symmetric quasi-equivalent to a distance is a quasi-distance. Okay, now here's another good thing. So this middle expression here, even though first you obtain it for smooth endpoints, it actually makes sense for endpoints in EP. And again, it's just due to the fact that on this space EP, Gedgen-Zeryahi worked out a lot of potential theory. So we know what makes sense and what doesn't make sense. So now, using this fact and this double inequality, you can show really fast that this dp distance, just by taking some sort of limit, you can define it for any endpoints, for any two potentials in EP, not just smooth potentials. Moreover, this double inequality will also hold in EP. Now, this still doesn't. Okay, so how does this get us closer to what the metric completion is? Well, if you just put 0 here, the 0 potential, which corresponds to the background metric, and an arbitrary potential p here, then you get that the dp distance is more or less the same as this expression. Well, in potential theorists know, right? So the LP norm of a plurisubharmonic function is always finite. And as a matter of fact, if you take normalized by supremum equal to 0, this thing is always under control. So the only thing that interacts with, I mean, the only interesting term here on the right-hand side is this one. But this is the quantity that showed up in the definition of EP space, right? So you get a very quite precise intuitive picture, right? So basically, the right-hand side is finite if and only if you're in EP. But that means what? That you're somehow at finite distance away from the background metric. So finite dp distance away from the background metric. So it's again, more and more pointing in the direction that you're doing the right thing. Because being at finite dp distance from the background metric is exactly the same as being in EP. Now, again, is this how you prove completeness? No, right? So if you want to show a space is complete, you're not going to get away Cauchy sequences, right? They're going to come up, and you have to show that their limit is in the space. Well, you need one more thing to do that. So to show that Cauchy sequences have limits inside EP, we will make use of this so-called minimum operator in EP. So you take two potentials, u and v. The maximum is always going to be, so you take two omega plurisubharmonic functions. The maximum of u and v is always going to be omega plurisubharmonic. This is a basic thing. Same thing for subharmonic, plurisubharmonic functions. But the same thing is not true for the minimum. Another basic fact. So what this P operator does is tries to find a replacement for this min of two potentials for which this is true. Now, this is not always possible in this generality, and this space is too big. But inside EP, you have a convenient replacement. So you take two potentials in this candidate completion EP, and you define PUV. Well, what's PUV? Well, I take the minimum, right? So I have U, this is U, and this is V, right? So this is the minimum. This is not going to be in EP, but the one thing I can do, I can take every possible potential here lying under this minimum and take the suprema. Okay, so one thing that's missing here, I'm missing a sup, right? So these are the candidates. So these are potentials in EP that lie below both U and V, and I'm taking the supremum of all of these. Now, it's a theorem to show that this this PUV, which, as I said, is the replacement of the minimum, is in EP. Typically, if you're just inside PSH X omega, you may not have a single candidate satisfying this inequality. I mean, just think of two, CP2 or CP1, take two potentials whose Laplacian forms a Dirac mass, right? There's nothing. Potentials, there exist potentials with having a Lelong number at a single point, but there are no potentials whose Lelong numbers is equal to 1 at two different points. In the compact case, thankfully, the singularities of potentials in EP are extremely mild, and that's what saves you here. But I'm still emphasizing, so it's not a triviality to show this, but at least you have a replacement for minimum. And the reason why this comes up as sort of important in this metric completion business, if you take three potentials, U, V, W, then the following contraction projection property holds, right? So why do I call it projection? So you can take the following operator, right? So take a potential from this space EP and now send it to PW U, right? This is also an EP. So what this theorem claims is that this is a projection operator in the metric sense or contraction. So the dp distance between the image of this operator is always controlled by the dp distance of what you started with. Okay, so why does this come up? Well, maybe you'll get a glimpse of it. So to show completeness, we need to do it with Cauchy sequences, right? No other way. So let's pick a Cauchy sequence in EP, and I want to show that the limit is also in EP. Well, there's two cases. The easy case is when this sequence uj is decreasing or increasing in the sense of potentials, right? So this is what I mean, right? So either you have uj plus 1 is less than uj, or the other way. So in both cases, it makes sense to pointwise define the limit, right? So this is going to be some u for every fixed point x ux. Right? So you at least can write down the obvious candidate for the limit, right? It's the pointwise limit of your potentials. And again, I'm not going to emphasize too much. The obvious pointwise limit is going to lie in EP. Moreover, you can show that this pointwise limit is actually the dp limit, because the dp distance from the uj's to u goes to 0. To do this, you basically go back to this expression, right? What you end up showing is that this expression, where the v is replaced by uj, goes to 0. And again, since we're dealing with monotonic sequences, finite energy potential theory, people that have studied these Gedge-Zariahi works know that there's very good limit theorems for monotonic sequences. That's what you throw in here, and then basically some arguments involving dominated convergence and things of that nature give you what you need. That you do have so your Cauchy sequence does have a limit in EP. Now, in the general case, that's difficult because now you don't have an obvious candidate to where your Cauchy sequence should be converging. And what you end up doing is you replace your sequence uj with a equivalent Cauchy sequence that's going to be increasing. Now, again, so for that, we will use this p operator. Now, before I explain what's in here, because I have maybe 2-3 more minutes than I thought I would have, maybe let me tell you that what's going to happen here is something that is the min analog of a classical trick that potential theorists use. If I can only find the eraser. Oh. It's interesting. Okay, so this is a trick that I saw in classical potential theory books. So you have an L1, so flat L1 limit of PSH functions, right? It's a well-known fact that when you look at the supremum of K greater than J, UK, right? Call this VJ, right? This is also, so everything is PSH here. Then VJ is also going to be PSH, right? And it's well known that the VJ will have the same L1 limit as the UJ. Moreover, these sequences are sort of Cauchy equivalent in this obvious manner, that this will be less than something, I don't know, so small j. Obviously, their limit is the same. Yes. Yes, USC, right? Right. Thank you. Okay. So again, what has happened here? Well, to an arbitrary L1, flat L1 limit, I associated another sequence, but this sequence is decreasing. So this is decreasing. So this was arbitrary, this one is decreasing, and they have the same limit. Now, here it didn't do any good for you, right? It didn't really help you because you know that L1 limits, if you have an L1 convergent sequence, then a subsequence is almost everywhere convergent, right? All right, measure theory was a long time ago, but that's still true. So, so here, L1 limits automatically imply that you have a pointwise limit. Not so much in our case. So that's what we will gain from here. So in this story, to wrap things up, again, so we have a general Cauchy sequence. So a general Cauchy sequence. I will associate to it a Cauchy sequence that will be increasing in this case. So you see what's going on here is I have the P operator here. So the P operator is essentially intuitively the same as me doing this here. Obviously, I can't do that, right? But if you could, then this would now be an increasing sequence, right? So what I do is basically do P, and then what you see here is essentially that, right? So you can take finitely many P's. So this is the minimum, the P minimum of the uj plus 1 all the way to uj plus k, and I let k goes to infinity. Now, you have to show that this limit exists. But again, you're in the good situation, right? this sequence here will be a decreasing sequence in EP. And it's, again, not hard to show that it's Cauchy. So by the first case, it will have a limit. The limit will be exactly this. And by using this contraction principle again, you wrap it up, right? So the sequence Vj, which is clearly increasing, you can write down what the pointwise limit is, and then it will dp converge to that. Moreover, the dp distance between the Vj and the Uj will go to 0, and then you will use this theorem for that multiple times. All right, so I don't want to abuse your patience anymore. Thank you very much.
Okay, so any questions?
It's because I know you have a nice theory of relative pure potential theory on compact element. So
Right.
So my question is, can the results hold for the prescribed singularity case?
Okay, so yes. Okay, so it's known to hold up to some generality. I think there's a version of this that should hold in the case of general model type singularities. I guess you know what that means.
Yeah.
Now, let me tell you what the difficulty is. There's an obvious difficulty here, right? So in case of those potential spaces, there's no really good analog of what this is, right?
Yeah.
So there's no space of smooth Kähler potentials that you extend. But there is a notion of EP spaces, relative EP spaces. So what needs to be done is to kind of pull the rabbit out of the hat and immediately define what dp distance is on the relative EP space. That's a little bit tricky. So what I've seen done, I think my collaborator Ming-Chen Xia worked on this, and also a little bit my student Prakar Gupta worked on this. But the only case that so far was penetrable was the case of I-model singularities.
I-model.
So those are the singularity types that can be approximated by algebraic singularity types. And for those, you can use resolution by singularities, subtract divisors, and then it kind of reduces to the smooth case. It's a long thing, but really it ends up being sort of a limit case of what I've done. But that's probably not the best way to do it. The best way to do it, perhaps, would be to just define these dp distances directly on the relative EP spaces. What that definition is, I don't know. But I suspect it should work. Maybe some ambitious junior colleague could work that out. I don't know.
Okay. My second question is, can this hold for the M subharmonic function as discussed in Professor Grodzi's talk?
Again, it's tempting to say yes, but in that context, I'm really not moving around comfortably. So I would just stop it with that answer.
Okay, thank you. Thanks a lot.
Other questions?
How can you exclude this minimum operator P is not identically minus infinity?
Not identically.
Negative infinity.
Yes. So you have to work a little bit. There's really no. I mean, it's an approximation result. It heavily depends on the fact that U and V are in EP. Maybe I can show it on the board after the talk if you're interested. So what's going on, and I'll just vaguely leave it at that. So this object, from a PDE point of view, it solves an obstacle problem, where the obstacle is the minimum. And so basically, What's that? Yes, I mean, I'm assuming everything is Kähler. Actually, all this works also even in the generality that he asked about. But it's best with the Kähler case. So what happens, the minimum is your obstacle, and PUV is the biggest plurisubharmonic function that you can push under here. Let's end up here on the place where they don't touch, right? This potential is under tension, and that simply means that there's no mass here. And this is what you sort of leverage to show that this thing must be an EP. But again, there is a bit of work. There's no sort of magic.
More questions? Okay, so if there is no further question, I think Professor Darvas or Guy